protecting yourself from the UV, the light. The more you are dense, denser, you collapse and then you form stars. Then, patati patata, stars, explosion, Okay. Then you vitamin bottle and amaro and stuff. So this is why it is important. Then you collapse, you form planets, etc. Right. So this is the life of a dust grain. هلا ليه ما سألتوني طيب the first dust كيف اجى؟ هيك كنت بدك تسألني؟ بعرفك انت نكد ما بدي اوقفك ما بدك توقفني انا وقفتني. Okay. So in Tamura, Italy, هيدا paper 2019 they discovered the first dust اللي فيه يكون مكون من iron or يعني crystalline or carbon من 13.2 billion light year. قد ايه عمره الكون؟ 13.7 billion light year. So means that by that time كان في star formed and exploded to form the dust. But until now it's not sure مين قبل. يا جيجي يا البيضة, we don't know. But I guess that ما بدي اقول what is my guess. Anyway, so just to tell you that this is a infrared detection for the galactic plane to show you that the dust is everywhere in the galaxy. So if you want to get rid of the dust, you have to wake up very early. So I hope that I convinced you that the space is a very, very dusty place. I will redo it because this is the end of a very big star. It's the Crab Nebula, my favorite one. It's a very important nebula. At the end, it will oscillate a little bit, collapse, explode. In the center, there is another source, a synchrotron source, not thermal, pulsar. And you see that we have filaments of dust. What's important in the dust is that they come by sizes and by flavors. Flavors مش يعني على خل وعلى هذا, no. By crystalline, carbon, and others. The crab is a very important one. It will show us how the dust will grow. The importance of the dust, studying the dust, will give me a direct information of the dark matter, because the dust will radiate into all wavelengths, the visible wavelengths, visible, detectable in the electromagnetic spectra. If you measure the mass of the things that we detect, we can measure the mass of the things we cannot detect. And then, the Crab Nebula is here. I just wanted to tell you, this is the galaxy, and the Crab Nebula is here. Why I'm talking about the crab? Because I love it. Okay. So, we talked about the importance of the dust in the molecules, in the planets. We discovered a lot of exoplanets, extraterrestrial planets. One of the methods is the transit. For example, now I'm transiting in front of the screen, okay? So I'm dimming the light of the screen. So from the light of the screen, you can know my height, my whatever is, my width, and from the timing of my transit, you can know how many times I'm passing. Okay, I know I have to stop it. Okay, fine. So this is a method that was used by Kepler, and we discovered a lot of exoplanets in our galaxy, a small part, tiny part of it. nature is so generous with us. The colors are the sizes and the temperature, and those are stellar system in our galaxy discovered by transit method. I didn't found a simulation like this for the 2019, but I will tell you later. All those are stellar system. And look please at the number of planets discovered since 1991. And why it's like that? Because Kepler observed in one spot, one small spot, and it rotates always in the same, to look at the same spot, okay? It's rotating like that by the rotation of the Earth with the angle 23.5. Those are the numbers. Look at the numbers from 1991 to 2005. هلا بتشوفوا. The colors are the method of detecting. It just emphasizes on the transit, but we have several methods. If you're interested, we'll talk about it later on. So, transit is the field of view of Kepler, where Kepler blew. So until 2019, we have 4,003, but this is the beginning. Until yesterday, we had 4,999 extraterrestrial planets discovered in a small spot in our galaxy. So to continue the legacy of Kepler, in 2021, if it will fly, we will have the James Webb Space Telescope, the biggest mirror ever sent in space to detect the exoplanets also, but not also. It will detect the first light after the ionization, and it will be deployed in space. This is the secondary mirror. It is 6.5 meter. Imagine Hubble did great things with its 80 centimeter mirror, and those are the shielding. They will open really in space, and just wish me luck, because I can lose my job if I don't have papers from James Webb Space Telescope. It will explode. And this is really, you see that the mirrors are like honeycomb, because how you will send a 6.5 meters into the space. So we need to do like this, to send it with a shuttle, and it will open in the space. I love it. We did a human size in space telescope in the Day of Science, the USG, exactly, and it was really fun. And the telemetry is here, and everything, the solar panel are here, and it will be at the L2, very, very far, 1.5 million kilometers from the Earth. It's 3 times the distance to the moon. And to finish, we're going back to the moon, and this is also a screenshot from the pictures of Maroon Habib, otherwise I couldn't have it. Let us go to the moon, and from there we go everywhere. Thank you so much for listening to me. Take the questions later on. Please, now we are going to welcome Dr. Luay, and can you please, Marie-Jo, present Dr. Luay, please? Thank you. Okay. Sorry, بعتذر. Sousan, please. Can you present Dr. Luay?
So our next speaker is Dr. Luay Abdallah. Dr. Luay Abdallah has his PhD in nanotechnology and nanoelectronics from the University of Grenoble in France, and he is working on launching the first nano-satellite from Lebanon called CubeSat, and he's going to talk all about it. The floor is yours. The floor is yours.
انت بتوزع شعار بس مش عندي التسجيل. مش انا بعطي
The pictures, yeah. Marwa? تعالوا هون.
This is the middle.
It's a middle. Girls? Hi. Girls? Hi. Can we move to the middle هيك لناخذ الصور كمان يعني هون شو محل.
Can we move to the middle because هول سائلين يلا please دكتور
Thank you for the introduction.
يلا go go.
Thank you for the introduction. Thanks, Dr. Cyrine, for the invitation. بس الصبية اللي عرفت عني ما عرفت.
سوسن.
Thanks, Dawson, for the introduction
You're
also.
welcome.
Okay. So my talk today is about the CubeSat technology. So first I would like to introduce the CubeSat concept. Just to be familiar with the concept, we are talking about something, let's say now it's a hot topic in space technology. So let's say engineers with the astronomy we can complete each other toward developing the first Lebanese nanosatellite. So, but we hope that Dr. Cyrine will have the time to collaborate with us.
Of course. هي جوز خلص.
Okay, great. Okay, so currently I'm senior engineer at Dolphin Design, so that's created by MBDA, Missile Systems and Soitec. So MBDA is like one of the company of Airbus Group. So, however, in Lebanon, I worked as a general coordinator of the Lebanese nanosatellite project that is funded by the European Union and managed by Crown Agents UK. We'll talk about this. Let's begin first by talking about the CubeSat concept. So when we say CubeSat, we are talking simply about a very small satellite. When we say a small satellite, let's say there is a 1U, what we call 1 unit. The 1 unit is like 10 centimeter by 10 centimeter by 10 centimeter. So it's one of the standard of a CubeSat. And the mass should not be more than 1.33 kilogram. So, and we can add a multiples of the basic CubeSat unit, and so we can have 2 unit, 3 unit, 6 unit, 12 unit, depending on the application that we aim to do, depending on what we want to do with, what's the characteristic, what are the services that this CubeSat can provide to the country or to the university or to any agency that is developing CubeSat. So why now we are talking about CubeSat? Because now we have these, so here I can give some examples. As you can see, it's examples of 1U or 2U or 3U CubeSat. We'll go later in more detail on what we can have within one CubeSat. But first, let's introduce the two persons that developed the concept of the CubeSat from Stanford University and Calif Tech University. So they developed the concept, and the aim of this concept is to help universities worldwide to enable students and researchers perform space science and exploration. Because the old space, what we call the old space, where Russia and USA were the only, let's say, nations or the big countries that only develop satellites, that only works on space technology. Now, in the new space concept, that is led by the CubeSat, the nanosatellite, the microsatellites, any country has the right and the capability to develop spacecraft, and by the support of many launch companies, the satellite can be launched into space on around 400 to 900 kilometers. It's on the low Earth orbit. So this is the concept. So we can see already we can realize that the concept already has been introduced only for universities, only for students, and the main point that we should stress is that within this very small system, we have a payload that can be dedicated for any astronomy application like the one that already presented by Dr. Cyrine. We can have a power system, so the electrical power department of any engineering school is concerned. It includes a communication system, so the communication department in any university is concerned. Mechanical structure, it's the structure of the CubeSat. We have the ACDS, what we call altitude control and determination. So here there is a lot of algorithm to identify and to detect towards the CubeSat and how to control it. So all the theory and math and algorithm that are developed inside such systems require the Faculty of Science guys, the math department, to develop such theories. And sure, the physics department is presented in all these systems because it's, for example, if we have a astronomy mission, so it's the physics department who define what is the mission. For example, if it's a science mission, so the physics department say, I would like to explore, I don't know, the gamma, for example, and then they will define the specification of the system. And then the engineers come and say, okay, we will develop what you need, for example. So we can see that all engineering and physics department are concerned. And this was the initial idea that was the origin of creating the concept by the two guys of Caltech and Stanford. But why now the CubeSat becomes very popular? Why now there is a boom of CubeSat? Why now in Lebanon, with the many problems that we have in Lebanon, we are discussing about developing a CubeSat? To answer the question, first we should ask themselves what's happened. Why now we are talking about new space? We are talking about this because there is standards that have been defined. For example, the 10 by 10 by 10 centimeter. For example, the 1.33 kilogram. When there are standards that are defined, the standards make something very popular. So when we standard all the system, so me in Lebanon or a guy in USA or a guy in Europe will develop exactly following the same rules, which was not the case in the past. So when we develop following the same rules, we can say, okay, so let's go together and put all these CubeSats in a single, what we call B-pod, and launch it to space. So all of us will pay the launch. So we'll not pay $10 million, we'll pay $80 kilos. You will see the cost later. So this was the main point, the standardization of all the rules of development satellite that reduce the cost, reduce the development time. Why reduce the development time? Because now I know that maybe someone will develop CubeSat 1U. So he needs a mechanical structure, let's say 10 by 10 by 10 centimeter. And he should use a mechanical structure with this material already defined